Okay, so now we get to the fun part. We get to derive this formula for pendulums. How in the heck do we get to this for pendulums? And why does it look so similar to the period for a spring? Well, because a simple harmonic motion is the answer to the last one. That's the easy one to answer, right? So 2 pi, one full cycle. Remember, 2 pi here is not necessarily how many degrees you've gone through. It's actually, if we're talking about amplitude over time, it's basically how many cycles you've gone through. So one full cycle, peak to peak, would be 2 pi. Okay? One full cycle is 2 pi radians. All right? So what we're going to do is we're going to talk about pendulums now. And this is an interesting thing. So let's think about let's consider the physics of a pendulum here. You start out with a string like this, hanging with a mass on it, and you stretch that back so that now it's at a new position over here, and you let it go. So it's got some kind of an angle that you change, right? You raise it up to a new angle, and you let it go, and it swings. Why does it swing? Because force of gravity is pulling us down. Why doesn't it fall? Because the force of tension is holding it up. But if you look, when it's on an angle like this, this is a pain in the butt. Because look, the force of tension is at an angle, and the force of gravity straight down. Those things are not canceling out, which is why a pendulum swings. Because while the y component is being canceled out by gravity, the x component is not. So it is a restorative force. It's trying to bring it back to where it wants to be, right in the middle, hanging freely, no movement. But this is the pain in the butt part because we have to figure this out. We have to figure it out for the x and we have to figure it out for the y, okay? So we don't really have any force in the x direction. The only force we give it is whatever force we use to pull it back. Where's my pendulum? Where's my pendulum? There's my pendulum. All right, so if I pull a pendulum back, gravity doesn't bring it up here. I bring it up here. And then its inertia will bring it over here, and then its inertia will bring it back to here, so on and so forth. So really, it's positioned backwards, right? It's positioned over this way, if I'm going to line it up with the board, right? The x force is me. I am the x force, okay? So on this, if we look at this, first off, for this piece, let's talk about the force of tension y and the force of tension in the x direction, okay? So for this, you have a triangle like so. If you want the x piece or the y piece, here's our force of tension over here. Well, we got to go back to our trigonometry, right? So over here, this is going to be sine, okay? It's got something to do with sine. It's the opposite side. And this is our adjacent. That could be better too. Adjacent side, okay? So it's going to have something to do with cosine because we know that sine of theta is equal to opposite over hypotenuse, right? So if we know the hypotenuse, we want to figure out the x piece of this. This is the force of tension in the x direction. We know the force of tension in the x direction. That is our opposite side. Our hypotenuse here is going to be the force of tension. To rearrange that to solve for f of t in the x direction, we get f force of tension times sine of theta will be force of tension in the x direction, right? Now, I can do the same thing with cosine over here, and what I'll get is force of tension times cosine of theta will give me force of tension in the y direction. Okay, so for our pendulum, that's where we find our components of force. I'm going to write those off to the side here and keep a hold of them, okay? So force of tension in the y direction is force of tension in the string times cosine of theta. Force of tension in the x direction is force of tension, or hypotenuse, times sine of theta, okay? And if we're going to do anything, we should really start with the easier piece here. Now, what's the easier piece, right? The easier piece is actually going to be the x to start out with, okay? Because we're going to have to get our main equation from that. It's going to have less terms in it. I'll show you why in a second. It'll become very apparent, okay? Well, let's start with the x. I'm going to go ahead and erase this for a second, okay? Let me redraw it in a smaller portion here. Notice we still got our main equations we cared about over there, okay? So, okay, I have a pendulum. We shall name him Fred. Okay, Fred the pendulum wants to be here. That's where he wants to be. But we're going to force Fred to be over here, okay? So there's Fred, right over there. And I used a force this direction, force of Mr. Casey, right? Why not? Okay. So that's the force I used. Now, there's going to be another force. The force of gravity is really going to bring it down. It's going to pull it back this way, and it's going to do this. That's the force of tension, right? The force of tension in the x direction is the part that's going to bring it back. It's the tension that's going to do it. So those two things have to be equal before I let it go, right? Once I let it go, well, that's a different story. But at the peak here, at the peak, those are equal for me to get it back to that point, okay? For me to get it back to that point, my force has to be equal to the force of tension on the string, okay? So F of t in the x direction has to be equal to F of Mr. Casey, okay? So force of tension here in the x direction we found out was, it's like when you're trying to answer true or false and you don't know the answer, you write both. I had the cross going all the way. Okay, let me get a better F on there, okay? It's totally, it's true false. Okay, no, okay, so, all right, so force of tension in the x direction is force of tension times sine of theta. And the force of me, what is that? Well, we don't know. But any force that you don't know is always a mass times an acceleration, right? So, cool, we've got that. Okay, what do we do now? Well, we can take and move this over. Why not, right? So, in fact, let's move this one over. So we'll get 0 is equal to ma minus force of tension sine theta. And this is starting to look like some simple harmonic motion stuff going on here, okay? So this, we got to remember, this is the second derivative of our position, okay? So that can still come back in here in a second. But we're going to pause. We're going to hold this one and leave it as it is, okay? It's for the x, okay? So I'm going to put for the x. For the x, 0 is equal to ma minus f of t. And you know what? I'm going to simplify this down a little bit later, too, or a little bit right now. Let's go ahead and do it now. Sine theta, remember what that is? That function, sine theta, was actually opposite over hypotenuse, right? And this, our opposite is our x, and our hypotenuse is our force of tension, isn't it? So, what we end up getting is, let me look at my notes here before I forget what the heck I'm doing. It's easy to do right now. Looking, forgetting. Ah, yeah, sorry. For our position here, right? For our position, instead of sine theta, our position is going to be the length of our string. Gosh, that is a terrible L. And our x direction, okay? So x position and L, x over L will get us our sine angle the same as our forces did, because that length, that hypotenuse, and that x direction still have the same relationship. So it's going to be the same as x over the length of our string. So I'm going to pop that in place of sine. So it's going to be the force of tension times x over L, okay? And I just got that from my sine theta formula. You know, I could write that better. How about that? That's still a little bit E-like, but less E-like, okay? So it's definitely an L for the length of the string, okay? All right, so that was X. Now for the Y, okay? So let's go back to looking at this in terms of forces again. Okay, so we found out for our X's what that would look like. Now, I can probably set this pendulum down so it's not just hitting the wall I do over and over again. Okay, so again, that pendulum was to be here. I pull it back to here, and the force now of gravity is pulling against the force of tension in the y direction, okay? Those are the two things that are happening for y, okay? For y, it is, the tension in the y direction is being counteracted by gravity, okay? So we can set those two things. Well, let's see here. You still have to pull it, don't you? You have to pull it up, okay? So I have to pull it up, okay? So it turns out the force of my pull is equal to those two forces combined, okay? Let me check my notes, because something is checking my brain right now that is not liking. Yeah, we're good. That's good. Okay. So, again, any force you have is just a mass times an acceleration. Force of tension here, well, force of gravity we know is mass times gravity. And we know the force of tension in the y direction, we already found that. It's force of tension times, good grief, my brain's shutting off, cosine of theta. There we go. So force of tension cosine of theta minus mass times gravity will get me the force of my pull. Okay, I have to pull against gravity, and tension is going to help me out. Okay? So, where does that get me? Where, oh, where, oh, where? Well, this is where things become slightly more interesting. Okay? What we have here now is we have to assume some things. We have to make some assumptions. And it turns out the first assumption we have to make is called small angle approximation. Okay? So use your calculators for this and you can find something interesting. Okay? If I start here and I've got a cosine, let's say, so cosine of 0 is 1, right? So I'll start out here, okay? So at my 0 point, I'll start there, okay? And if I go on, then it does something like this, right? Okay, well here's the thing. Cosine of 0 is 1, but what is the cosine of, say, I don't know, instead of, if it's all the way up here, let's say cosine of 0 is equal to 1, but what is the cosine of 10 degrees? Well, it turns out it'll be very, 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 very close. It'll be extremely close because right now, that curve at these points is actually very flat. So it takes a little while before you get a noticeable or appreciable difference in your value. So with physics, we like to fake things. This is not mathematics, right? So with physics, we're going to fake it. And the way we're going to fake it is say that we're going to be within like 1.5% on our value, even if we're 10 degrees off. So even for 10-degree angle, you're still pretty dang close to the right answer. So for physics, good enough, okay? Mr. Ellis will kill me when he hears that. But you know what? He knows about this too, okay? So we use a small angle approximation. Anything that's like 10 degrees or less, 10 degrees or less is basically equal to 0, okay? Basically no real difference. So really pendulums, okay, and this is the important thing, they only work for small angles. You get to a high angle, some weird stuff starts to happen. It becomes less accurate. So you have to keep that pendulum on a small change, right, in degrees from its 0 point, okay? So that's the first thing we're going to use, small angle approximation. Okay, now we're going to make another assumption. We're going to take and assume that we're going to start from an interesting place, okay? The interesting place that we're going to start from is actually going to be up here at the peak, okay? So if we consider it from this start where we actually pull it back to, which kind of makes sense, right? You have to pull it back up to that point. Well, what's the acceleration at that point? Well, watch, it comes to 0, right? Everything kind of stops there. I guess the acceleration still keeps happening, but basically it's 0. If you assume that y double prime, okay, or acceleration in the y direction is equal to 0, what can we get? Well, what we have so far is we can assume that our angle is basically 0 because we have, a small angle approximation. It's close enough, close enough. So cosine of 0 is 1, right? So assume that we've got that is 0, and cosine of theta, well, is cosine of 0 degrees, okay? Close enough. So that's equal to 1, all right? So now let's plug it in up here, okay? What do we get? It turns out what we get is our mass times our acceleration. Well, our acceleration is 0, right? We assumed that one. So that means this whole side is 0, right? And that's going to be equal to force of tension in the y direction. Force of tension times cosine of theta. But cosine of theta here we're assuming is 0 is theta. So we get times 1, okay? So then we get minus mg. And look at that, that's also starting to look like some simple harmonic motion stuff now, isn't it? Okay, but let's take this one step further. Let's go ahead and solve for the force of tension here because now we can do it. We have another term in here to do something with, okay? So let's solve for our force of tension. Okay, so bring the force sorry, bring the mg over, good grief. Okay, so we get mg is equal to, false, right? Force of tension. And it was times 1, but again, anything times 1 is still itself. So we get, those two things are the same. Now that is where things are getting interesting, okay? So let's go ahead and plug that right there, what we just found. All the stuff that we went through with the y direction was only to get an equivalency so we can substitute something in. Like I said, take a deep breath on this one, right? Okay, so we're going to plug in mg in place of t for the x, okay? So for the y, what we found was force of tension is equal to mg. Okay, so now we're going to plug that in for this guy on the x. Ready? Okay. Let me get my highly expensive, very technical marker here. Okay. And let me go ahead and plug this in. Okay. Don't forget your small angle approximation. All right, so on this one, we're going to take what we found for y, plug that value in here for force of tension on the y. So for x, we will get 0 is equal to ma minus mg times x over length of the pendulum, okay? And look, mass in two places. So if I go ahead and I just bump this one over to the other side of the equation, right, we get that. Mass is on both sides, so it cancels out. Turns out our acceleration, what we get for that, is gravity, this x, and the length of the pendulum. Okay, so now that is interesting. Okay, that is interesting. And if you remember, what we're going to do now is we're going to take the same thing we did for the spring. Acceleration with respect to time was equal to omega squared, negative omega squared, don't forget there's a negative there, but easier to see maybe, negative omega squared times x. Okay, so now I'm going to plug that in place of acceleration. Another substitution, everybody loves them. Negative omega squared x is equal to gravity over length times x. And now we get an x on both sides, and that could go away. It just gets simpler and simpler and simpler, right? Okay, so now what I'm going to do is this, if I want to find omega, I'm just going to ignore the sign for now because gravity should also really be negative, right? They're both negative in direction. So I'm going to get rid of that, okay? Cancels. And if I want to find omega, square root both sides, and that's what we get. Now, that looks a lot like what we found for a spring, doesn't it? Our omegas are starting to look similar, but we want to go one step further. We don't want omega, we want our period. And I still don't need to have this pendulum in my hand, so why do I have that? That's a good question. Okay, so omega, remember t is equal to 2 pi over our angular frequency. So if I plug this in place of that omega now, another substitution, right, we will end up with t is equal to 2 pi, okay, 1 over omega, so flip that upside down, right? 1 over omega would just be that flipped on its head. Square root of L over, that is an L, not an E, L, good grief, that just looks like a bigger E. Guys, I suck at cursive apparently. Okay, so L over G, which is totally clear now. I'm going to go ahead and rewrite that so that it's actually clear to see. Period of a pendulum is 2 pi times length of the string over gravity. And it's at an angle, but deal with it because that's what I got, okay? Put a box around it so you can see. That's what I'm talking about right there. Okay, I'm going to get rid of this piece so it's easier to look at, okay? And look, boom, boom, you got period of your pendulum. And again, the other thing I want you guys to see is this. The thing on top is the thing you can easily change. You can change the length of the string pretty dang easily. It's extraordinarily hard to change the gravity of the Earth. So, thing you can easily change, thing you cannot easily change, okay? And that's it. That is our simple harmonic motion.